Okay, so in this video we're going to finish up talking about the gravitational force. In the last video we talked about the concept of the gravitational force, and we also talk about Newton's law of gravitation. And just to remind you, Newton's law of gravitation is an equation that looks like this. We have g times mass 1 times mass 2 divided by r squared, where g is called the gravitational constant, and the value for that is about 6.67 times 10 to the negative 11. M1 and M2 are the masses of the two objects that you're calculating the force between, and then R is the distance between mass 1 and mass 2. Okay, and so this type of relationship, as you can see from the equation, because you have distance squared on the bottom, this is what's called an inverse square relationship. Okay, it's called an inverse square relationship because well, like I said, the distance is on the bottom of the equation, meaning that as the distance gets bigger, the force of gravity gets smaller. Okay, that makes it an inverse relationship, and it's a square relationship because the distance is being squared in the equation. And so what that means is that there's a very specific type of relationship between distance and force of gravity. Okay, and so we know what the graph for that looks like. This is a graph of an inverse square relationship. Okay, this is another graph of an inverse square relationship. Okay, and you need to be able to recognize the shape of that relationship or the shape of that graph on future test questions. Okay, so basically what I'm saying is that not only does the force of gravity get smaller as the distance increases, but it does so in a really specific way. Okay, and so what I mean by that is if you take two objects and you double the distance between those two objects, the gravitational force is going to decrease by 1/4. Okay, now at first that might be confusing because you might think, well, if you double the distance is on the bottom, so shouldn't the force be like half the size of the original force? Why is it 1/4? And the reason is, if you look at the equation, g m1 m2 over r squared, because distance is being squared in the bottom, you have to take into account that squared. Okay, so doubling means basically something increases by a factor of 2. And if you take 2 and square it, you get 4. Okay, and so if you have two objects and you double their distance of separation, the force of gravity decreases by 1/4. If you triple the distance between two objects, then the force of gravity would decrease by 1/9. Okay, here would be 1/9 because 3 squared is 9. And then if you were to quadruple the distance between two objects, the force would decrease by a factor of 16, and so on and so forth. Okay, and so you have to take into account the square when you're doing those types of problems. Okay, now these types of problems that we're about to see are called proportional reasoning problems, and they're basically math problems. And basically what they're asking you to do is they're basically saying, okay, so if I change this variable by this much, how does this other variable change? Okay, so let's take a look at that now. Okay, so solving proportional reasoning problems. And again, this is really more of a math problem than a physics problem, but it's a math problem involving physics equations. Okay, so this type of problem asks you how one dependent quantity, for example, the force of gravity, changes when you change one or more independent quantities, or I should say how one dependent variable quantity changes when you change one or more independent variable quantities. Okay, so for example, we might have a question where it says, how does the gravitational force between two masses change if the distance between the two masses double? Okay, now, either you could happen to remember the answer to that because we did talk about it on the last slide. We know that the answer should be that it's 1/4 of its original amount. Or another way to approach that is basically to take the equation and make up numbers to plug into the equation. And so we're going to do some examples of this proportional reasoning right now. Okay, so here is an example question. Really, this is the type of question that you might see as like a multiple choice question. Okay, so the question says, the gravitational force between two masses separated by a distance r is Fg. What would the gravitational force between the masses be if the distance between them was double? and then the answer says express, or the last sentence says express your answer in terms of Fg. Now what that last sentence means is basically we want to know, okay, if we double the distance, we're going to get a new force of gravity, and we want to know what multiple is that of the original force of gravity. Now the easiest way to do a proportional reasoning problem is just to make up numbers to plug in. Okay, and so we know what the equation is. Fg is equal to g m1 m2 divided by r squared. And the easiest number to plug in any situation is just 1. Okay, so what I'm going to do is I'm going to plug in 1 for every single variable. Okay, I'm going to make g1, I'm going to make all the masses 1, I'm going to make r1. And if I do that, I get 1 times 1 times 1 divided by 1 squared. That's just 1. Then, here's what I'm going to do. I want to find my new force of gravity and see how that compares to the original force of gravity. Okay, but I need to make a change because the question says, what if the distance between them was doubled? So now I'm going to, keeping my original numbers, I'm going to make those changes. So if the distance between them was doubled, but everything else was the same, my new force of gravity would be 1 times 1 times 1 divided by, now r is going to become 2. Because if I'm doubling the distance between them, that means r is going to be 2 instead of 1. So now I'm going to divide by 2 squared. 1 times 1 times 1 is 1, and then 2 squared is 4. Okay, and so if you compare 1/4 to my original answer of 1, we see that my new force of gravity is 1/4 the original value. Which of course you could have just known if you memorized the graph that was 2 slides back. But this is how you would do that type of problem from scratch. Okay, so because the distance is being squared, when we double the distance, we actually decrease the force of gravity by 1/4. Okay, and so that is the easiest way to do a proportional reasoning problem, is just to make up numbers, plug in the numbers, and then make the changes they tell you to make. Okay, so we're going to do 1 or 2 more examples of this type of problem so that you understand how to do it. Okay, so pause there if you need to look at that some more. The answer to the question, by the way, just to be clear, would be this. Anytime it says express your answer in terms of Fg, that means your answer should have Fg in it. Okay, so the answer to the question is 1/4 times Fg. Okay, in other words, 1/4 of the original force. Okay, so let's take a look at another example. I'm going to call this one example 2. It says the gravitational force between two masses separated by distance r is Fg. What would the gravitational force between the masses be if the distance between them was increased to 3r? So in other words, the original distance was r. Now it's asking what would the gravitational force be if the distance was increased to 3r. In other words, if the distance between the two masses was tripled. And again, we're told to express your answer in terms of Fg. Okay, so see if you can figure out the answer to this question on your own. Okay, so I'm going to start by writing down my equation and then plugging in numbers for everything. I'm going to plug in 1 for everything because that's the easiest thing to do, of course. Doesn't matter what numbers you plug in, but 1 is the easiest number to choose. Okay, and so that would be 1. And now I'm going to write my equation again to find my new Fg, but I'm going to make the changes they want me to make. Okay, so everything stays the same except instead of r, it's going to be 3r. So that means instead of 1 squared, it should be 3 squared. So 1 times 1 times 1 is 1, and then 3 squared is 9. And then you compare the two answers. This is 1, this is 1/9. So the answer to the question should be 1/9 times Fg. Okay, in other words, if you take two objects and you triple the distance between them, the force of gravity decreases by a factor of 9. Okay, it becomes 1/9 the original value. Okay, so pause it there if you need to look at that some more. Okay, so let's see. I'm going to do two more quick examples. This is going to be example 3. Okay, again, see if you can do this type of question on your own. Okay, and the setup for this question is the exact same. The only thing that's changed is now the distance is not getting bigger, but it's actually getting smaller. Because here it says the distance between what was decreased to r over 2. In other words, the distance was decreased by half. So again, I start with my equation. I make up numbers to plug in. Again, I'm going to use 1 for everything. Keep in mind, I'm not actually calculating force of gravity here. What I'm doing, because this is a proportional reasoning problem, is really I'm not interested in the actual force of gravity. I'm interested in how the force of gravity changes if I change this other thing. By, like, what ratio does it change? Okay, so that's 1. I have Fg dash. This is my new force of gravity. Again, I go to my equation. I'm going to make the changes they want me to make. So instead of r, I'm going to put r over 2. That means I do 1 times 1 times 1 divided by, now instead of doing 1 squared, I'm going to do half of 1, which is 0.5 squared. And if you type that into the calculator, you do 1 divided by 0.5 squared, you should get 4. In other words, the answer to the question is 4 Fg. So what I'm saying is, if you decrease the distance by half, you're going to quadruple the force of gravity. So if you take two objects and you bring them closer together, it makes sense that the force of gravity would get bigger. Okay, so here our new force of gravity is bigger because the objects are closer together. Okay, so let's see one more quick example. And here in example 3, it's changing a little bit because now we're not going to change the distance, we're actually changing the masses. Okay, so example 4 says the gravitational force between two masses separated by distance r is Fg. What would the gravitational force between the masses be if each of the two masses was doubled? Okay, so this one is a little bit different. Okay, so again, we start with our equation. Again, we make up numbers to plug in. I'm going to put 1 for everything. Now, I go to my new force of gravity, and I make the changes they want me to make. Okay, so I have g m1 m2 over r squared. Now, the changes they want me to make, g is the same, but now mass 1 is going to be doubled. Mass 2 is also going to be doubled because it says if each of the two masses were doubled. And the distance is still going to be the same. Okay, so 1 times 2 times 2 is 4, divided by 1 squared is still 4. So my new force of gravity is going to be 4 times the original force of gravity. Okay, so in other words, if I double each of the two masses, it just, each doubling also doubles the gravitational force. So because I double each of the two masses, the force of gravity is going to be 4 times bigger than it was originally. Okay, so that is the answer to example 4. Pause there if you need to look at that some more. Okay, the very last thing we're going to talk about in this section of the unit is orbits. So as we've talked about before, the gravitational force is responsible for the tides, it's responsible for the orbits of the stars and the planets, it's what holds solar systems together and galaxies together and so on. Okay, now the shape of most orbits is what's called an ellipse, which is basically a mathematical term for oval. So I want to show you a simulation involving the force of gravity. Okay, so here is the Earth going around the sun, and I'm going to make it so you can see the path of of the Earth around the Sun. I'm also going to speed up the simulation. I'm also going to make it so that you can see a blue arrow, and this blue arrow represents a force of gravity. Notice, by the way, that the direction of the force of gravity is always towards the center of the circle because that's what's providing the centripetal force in this situation. We talked about centripetal force last semester. Okay, there's two blue arrows here because there's actually two forces that are equal and opposite because of Newton's third law that talks about like equal and opposite reaction forces. I'm also going to include a red arrow, and this red arrow represents the velocity of the Earth. Notice it's always going along the outside of the circle. Okay, now here, this really is a circle. This is not really an ellipse. It looks really close to being a circle. So I'm going to make some changes. Okay, and I want you to see how the changes I make affect the motion of the Earth. Okay, I'm going to increase the mass of the Sun. And when I increase the mass of the Sun, the force of gravity is also going to increase proportionally. Okay, so watch what happens. Okay, so by changing the mass of the Sun, I've changed the orbit, and now if you look at the shape of this orbit, now you can see it's not really a circle anymore. It is kind of like an egg shaped. It's like an oval. It's an ellipse, is the technical term. Okay, I want you to pay attention to two things. Number one, the force of gravity, and number two, the velocity. Okay, so let me turn off this arrow. Pay attention to how the blue arrow, which represents the force of gravity, changes as the Earth gets closer to the Sun. Okay, so hopefully you can see that as the Earth gets closer to the Sun, the force of gravity gets bigger. And then as it gets farther from the Sun, it gets smaller. Which is exactly what we've been talking about for two videos, so that should make sense. Now, let's see how the velocity is affected. Okay, so this red arrow is the velocity of the Earth. Okay, and so notice that the arrow gets shorter as the distance gets farther away, and then as the Earth gets closer to the Sun, the arrow gets longer. And you can actually see, even if I take the arrow off, you can kind of see the Earth speeds up, it picks up speed as it goes closer to the Sun. Okay, and so the takeaway that you need to take away from looking at this is that the closer an object is to whatever it's orbiting, the faster it's going to move. And the reason for that is because the closer the distance, the stronger the gravitational force. And so the stronger the gravitational force, the stronger the centripetal force, which means the speed is also going to increase. Okay, and so that's consistent with the last unit that we talked about. Okay, and so that is what your takeaway needs to be. Closer the planet is to the Sun, the faster it's going to be moving. And the farther away it is, the slower it's going to be moving. Okay, so let's take a look at two quick examples and we'll be done with this video. Okay, so this example, which is example 5, says, looking at the chart on the right, predict which of these planets will have the greatest orbital velocity and explain your answer. Notice the mass of the planets don't affect how fast they move. Okay, so I've made it a little bit bigger so it's easier to see, but these are the planets starting from closest to the Sun to farthest from the Sun. Based off of what we just talked about, which of these planets is going to have the greatest orbital velocity and which is going to have the slowest orbital velocity? So see if you can figure out which of these planets is going to have the greatest orbital velocity. Okay, and of course, based off of what we just talked about, like literally on the last slide, the closer the planet is to the Sun, the faster it's moving. Okay, so here you can see the full chart where you see Mercury actually has the highest orbital velocity. It's moving the fastest because it's closest to the Sun. Okay, so Mercury is moving 47.4 kilometers per second, whereas Neptune, which is the farthest planet from the Sun, is moving the slowest. Okay. And again, the reason for that is because the farther away you go, the weaker the force of gravity gets. And the weaker the force of gravity, that means there's less than triple the force, which means that the velocity also decreases. Okay, and then this is the last example in this section of the unit. The ISS, the International Space Station, orbits the Earth every 90 minutes. If you wanted a satellite to be what's called geosynchronous, which means that it orbits the Earth once every 24 hours, where would its orbit be in relation to the ISS? Closer or farther? Okay, so in other words, we have the ISS. Okay, it takes 90 minutes to go all the way around the Earth. In other words, the period of revolution for the ISS is 90 minutes. If we want a satellite to take 24 hours to orbit, does it need to be closer to the Earth than the ISS or farther than the ISS from the Earth? Okay, so see if you can figure that out. Okay, so the answer to the question is farther. Okay, and the reason is that the farther away it is from the Earth, the longer it's going to take to orbit because it's not going to be moving as fast. Because as you get farther from the Earth, force of gravity gets smaller. That means the velocity also gets smaller. Okay, so if we want it to take a longer time to orbit, we want to make sure it's placed farther out from the Earth. Okay, so the ISS is actually pretty close to the Earth. That's why it orbits the Earth every 90 minutes. Satellites that are geosynchronous are placed farther out away from the Earth. That way that they take a longer time to orbit. And by the way, if you're wondering what a geosynchronous satellite is or why you care about that, if you have satellite TV, those satellites are in orbit in a geosynchronous orbit. Okay, and so basically they're made so that as the Earth spins around, the satellite also goes around the Earth at the exact same speed, and that way the satellite that your satellite dish is pointed at is always pointed at the same location in the sky. So that way, if you want to watch satellite TV, you don't have to go out and adjust your satellite every day. You can just point at one spot in the sky, and that satellite is always going to be in that one exact location because it's a geosynchronous orbit. Okay, so there you go. All right, so that is it for the force of gravity. In the next video, we will move on to talking about electricity. As always, please let me know if you have any questions, and I'll see you guys in the next video.